Good morning. Today we are going to discuss about the transmission line parameter calculations. Actually, they have given model and transmission line performance calculations of transmission lines. They have given in the GATE syllabus. Before going to the performance of the transmission lines, we are going to study about what are the line parameters which are affecting the transmission line calculations. So, first we will study about the transmission line parameter calculations. The main outline presentation of our today's presentation is basic structure of power system, conductors, transmission line model, calculation of inductance, calculation of capacitance, previous gate problems, and the work for students. And what is the basic structure of a power system? And everybody knows that the structure of the system consists of generation, transmission, and distribution. In the previous class, yesterday's class, I have explained what is meant by generation and what are the types of generation, and after generation, how the voltage is increased to transmit and to distribute the voltage or power to the consumer points. Yesterday I have explained, and some of the comments I have received from yesterday's class is some of the topics are not in syllabus, but actually while asking, I have observed in previous question papers. In that question papers, they have given some of the factors like load factors and other things. So to explain that load factors and other things, yesterday's class I have mentioned some of the factors which are going to be defined to know the load, how the load is distributed and how to calculate the load and other things. So yesterday's class I have given only just for 10 minutes that load factor and plant use factor and other factors. That is actually all the members has to know that type of characters. That's where that type of factors. That's why I have explained in the last class. And today I am going to explain that, and last class also I have given that what is the basic difference between the DC transmission and AC transmission, and what are the levels of voltage in transmission and distribution. Last class I have explained, and this today's class I am mainly concentrating on the transmission part. So here you can see that in this figure we are having generation, transmission line, and distribution system. Whatever the generation it is going to generate, the voltage that will be stepped up. Generally the small voltages are going to be generated, and that will be stepped up with a transformer T1 to a large values of voltage to transmit the that voltage in the transmission line. Why it is so is to minimize the losses. We need to increase the voltage level for a transmission. Then again, for example, here around 22 volts is going to be generated. That will be stepped to a 400 kilovolts, and again this 400 kilovolts is going to be stepped down to 66 kilovolts. This transformer via transformer 2 T2. So why this 400 volts to 66 volts is going to reduce is the loads like industrial loads and factory loads. Those who are using power rating of more than 50 kilowatts. So more rating loads, they can utilize the power after stepping down the voltage from 400 to 66 kV, and actually these consumers, the consumers, those who are connected in between this T22 and the T3 are known as the sub-transmission consumers, sub-transmission line consumers. Their working voltage is around 66 kV, and their load is also more than 50 kilowatts. And basically these type of consumers will have their own substation at their premises, and they will reduce their voltage levels according to their requirement. So these are generally this is outskirts of the city. they will place this type of consumers. So from the T1 to T2, from the transmission voltage 400 kV to sub-transmission voltage level come down to 66 kV by using this transformer T2, and this 66 kV that voltage is going to be again stepped down to 33 kV, 11 kV, like that, using transformer T3. And here most of the consumers, like this type of after T3, whatever the network is there, that is known as distribution network or distribution system. And in this distribution system, it's a mixed number of consumers will be there, like different types of consumers, like commercial consumers, domestic consumers, and small scale industry consumers. All these type of consumers will be there. So these consumers will utilize the voltage. Let us consider the commercial customers. So they will utilize the voltage levels from 11 kV to 11 kV or below 11 kV, like 400, 440 volts, like that. So three-phase supply also. And domestic consumers will be utilized a single phase or three phase. The single phase voltage is only 220 volts, and three phase voltage is around 450 to 440 volts. So these type of consumers will be connected to the distribution system. And here already we know that transmission line will not have any tapping or any distribution of loads. Only distribution system side will have some distribution of loads and consumers tapping of loads, and sub-transmission line also will have a tapping of loads. These are the big load consumers, and these are the small load consumers. This is the general structure of the power system. So then what is the necessity of transmission line? You know very well that it's to transfer a bulk amount of power, whatever generated at the generating station. And but this bulk amount of power need to transmit with economical basis. So you have to select the conductor and the size of the conductor and material of the conductor and the type of the conductor, whatever may be. It's all this depends upon the amount of power that needs to be transmitted with economical condition. So because of that, we have to calculate the parameters of the transmission line, how these parameters will affect the power transfer. So for that case, before going to that, the parameters once again depends upon the type of conductors. That's why we are going to study about the type of conductors. The mainly type of conductors are four different types. One is the solid conductor, other one is homogeneous standard conductors, another one is composite standard conductors, and bundled conductors. Here, solid conductors. So solid conductors is basically homogeneous. It's only single conductor, single piece of conductor, and it is in a circular shape. Generally, conductors is always considered as in a circular shape in condition because of many advantages. Like these conductors may be of copper or aluminium. It is having high mechanical strength and tensile strength. So because of circular cross section, you can see that circular solid conductor will be preferred to make electrical field same throughout the surface of the conductor. So because of in circular condition, we can able to make the field, electrical field which is enclosed in this conductor is uniform. So because of that, circular in shape is going to be considered for the conductor. Then next thing is there is no application of solid conductors as transmission lines. For the transmission lines, the solid conductors cannot be used because this is a single piece of conductor and which will carry less amount of voltages, not the big amount of voltages. That's why solid conductors cannot be used for the transmission line. If we use also, the losses will be more. That's why they will not prefer for transmission lines. Then flat or solid conductors are used for power transformer winding. These applications of solid conductors is mainly for power transformer winding of the power transformer. So these conductors are generally used for power transformer winding. The next type conductors is homogeneous standard conductors. So here number of strands are taken and are twisted together to increase the current carrying capacity by maintaining the same operating voltage. That means the same material itself will be used to have many strands. Many strands means many number of conductors which are connected together, are twisted together, so that the total current carrying capacity of that conductor will be increases and voltage will be maintained constant. So all standards, this type of standard conductors, homogeneous standard conductors having the same material, either copper or aluminum, then compared to standard conductor, it is having high mechanical strength and low tensile strength. Compared to the previous, like the solid conductor, this is still further is having high mechanical strength and low tensile strength. Then stringing is easy in standard conductor, so transportation is easy. Generally, this type of conductors, stringing means that flexibility or twisting or whatever maybe it is, this stringing condition, like bending, like the transportation and all, it is very easy. So this type of conductors are more useful for high current rating than solid conductors. Then composite standard conductor. Composite standard conductor is nothing but it is one similar to homogeneous standard conductor. There a similar material will be used. Here we are going to use different types of materials for different layers of the conductors. So here standards of different material are twisted. Different materials are twisted together to form the standard conductor. Its purpose is to improve the tensile strength. The main thing is improve the tensile strength. Generally, the example for this type of composite standard conductor is aluminum conductor, steel reinforced. Aluminum conductor, steel reinforced conductor. Generally, you will see in laying of cables or transmission lines. So here two types of materials they have used. One is the steel, other one is the aluminum. So here layer wise they will connect it. Each layer is counted with the number of conductors like the standard. So initially it will start with 1, next it will start with 6, next it will start with 12, next it starts with 18, next it starts with 24. Like that number of layers will be connected and this type of conductors are more useful and having high tensile strength. So if suppose D is the diameter of each conductor, N is the number of layers, then the diameter of the standard conductor is, then D is the diameter of each conductor, D is the diameter of each conductor, N is the number of layers, then the total diameter of this type of composite conductor is 2N minus 1 into D. 2N minus 1 into D. So like this we can, depends upon current carrying capacity, we can increase the diameter and layers of the conductor. Layers of the composite conductor. And then these conductors generally represented, the standard representation is X by Y, where X is the number of aluminum strands or steel strands, Y is the similarly number of aluminum strands or steel strands. Like power conductors, this X by ratio is greater than 1 or less than 1, like that they will consider X by Y is less than 1 or greater than 1, like that. That means that aluminum strands are greater or steel strands are lesser, like that. So depends upon the requirement, they will do the number of layers and the number of conductors. Then next thing is bundled conductor. Nowadays this is the advanced type of conductor. Everywhere they are using this bundled conductor. The main advantage of this is if the voltage rating is greater than 230 volts, this is the most suitable type of conductor. And if the voltage increases to 30 volts kV, what is the problem we are going to face is the corona loss and the interference with the communication lines is more. The corona loss means the ionization of the gas. The ionization of the surrounding medium of the conductor increases. Due to that, the potential, see that the corona occurs when the surface potential gradient of conductor exceeds the dielectric strength of the surrounding air. This causes ionization of the area near the conductor. That means corona means what exactly is the surface potential gradient of conductor exceeds the dielectric strength of the surrounding air. Because of that, the surrounding air is going to be ionized and it acts as a conductor. So due to that, nearby conductors will have a problem, and that you can say that interference with effect will be there. So due to that, this other than bundle conductors, if we use this losses, corona loss, and interference with the communication lines will be increases due to that, due to this large values of voltage. So to avoid that, what we are going to use, we will modify the conductors with a different type of materials, and different type of materials with a different number of conductors. So that the high voltage, here they have given that what is meant by bundling. So the high voltage surface gradient is reduced by using 2 or more conductors per phase in close proximity. That means more than 2 or more conductors per phase. Previously, we are using a single conductor per phase. Instead of that, now per phase we can increase the number of conductors so that the voltage gradient will be reduces, and the 2 and 3 conductors are connected such a way that looks like a single conductor. And this type of conductor, this type of connection is known as a conductor bundling. This is called conductor bundling. So the conductors of bundle are separated at regular intervals with the spacer dampers that prevent clashing of the conductors and prevent them from swaying in the wind. That means oscillating, like oscillation. Conductor to conductor, that oscillations can be avoided by using these spacer dampers and clashing, prevent the clashing by using these spacer dampers. So, what is the main purpose of this bundled conductors is to avoid or to reduce the corona loss and interference with the communication lines. We are going for the different type of conductors known as bundled conductors. These bundled conductors will have a 2 or more type of conductors per phase is connected in close proximity. Then how they are connected, we can see that in the diagram. This is one conductor, this is another conductor, this will be connected. It is a 2 conductors per phase. These 2 conductors are connected like this, and this can be called as a group conductors or bundled conductors. Similarly, 3 conductors they will connect it. Similarly, 4 conductors they will connect it. This is one type of bundle conductor. This is another. This is another type of bundle conductor, and this is another type of bundle conductor. So many number of conductors we can connect it like this. So you will get that bundle conductors, and their calculations like GMR and GMD. We can able to calculate these things already. Maybe I will explain later also this. What is meant by GMR? It's a self GMD is nothing but the distance between these 2 conductors we can calculate, the distance between these 2 conductors will be calculated, and you can able to find out that what is the total distance. It's a mean radius, geometrical mean radius we can able to calculate. That geometrical mean radius will be like this. We can say that what is the distance between each conductor and the actually the diameter of this conductor and the distance between this conductor will be taken as like this. So we can able to get it this, and similarly this, the diameter of it and distance between the conductors. That how many conductors we can have, that many conductors is cube root of that. And similarly 3 conductors we can write it like this. These calculations already I have studied in your BTech course, and later also I will explain how you are getting all this. Geometric mean distance, geometric mean radius. Then once you know that the type of conductors, and next thing is how we will model the transmission line. So the transmission line is modeling is always depends upon parameters of the line. So the transmission line has mainly having the parameters like resistance, inductance, and capacitance and conductance. Here the resistance is due to property of conductor that opposes the flow of current. This is well-known definition. Inductance due to magnetic field around the conductor. Capacitance due to electrostatic field around the conductor. And the conductance is also the capacitance effect. Sorry, conductance is the resistance effect. The resistance of the transmission line conductors is the most important and cause of power loss in transmission line. The main importance of resistance is mainly because of presence of resistance, the losses are going to occur in the transmission line. How that loss is depends upon, or what is the value of resistance is, that is resistivity of the conductor into length of the conductor divided by the area of cross section of the conductor. So for the conductor, the resistance can be calculated like rho times L by A ohms, and this value of R mainly cause for the power loss in the transmission line. Then this resistance again depends upon temperature. So at temperatures changes, then that resistance also will vary. So for T1, T2 are the two different temperatures, the resistance will be R2 and R1. If you observe that alpha is the temperature coefficient at temperature 1 at temperature T1 degrees. So that alpha 1 is nothing but alpha naught by 1 plus alpha naught. Alpha naught temperature coefficient at 0 degrees centigrade. So this is the resistance at temperature T2 is nothing but resistance at T1 into 1 plus alpha 1 into T2 minus T1. So this is the resistance of the conductor at different temperature. So mainly this because of presence of resistance, the losses are going to be exist in the transmission line. These losses will be dissipated in the form of heat. Then inductance of a two-wire line. The inductance of transmission line is defined as the this is already you know very well that why the inductance will exist is due to the magnetic field surrounding by the conductor. So that the inductance of the transmission line can be calculated depends upon the number of flux linkages per ampere current flowing through the conductor. Suppose 1 ampere current flowing through the conductor, how much flux is going to be, or flux linkages is going to be produced in that conductor. That ratio, the flux linkages divided by the amount of current passing through the conductor will give the value of inductance. So L is equal to lambda by I. And this is a simple calculation. So if suppose we are going to consider that a single conductor or two-wire conductors, two-wire line conductors, this type of conductors means you have to calculate the inductance of that conductor. So how you are going to find out the inductance? To find the inductance, the main aim is to find out the flux linkages. So to find out the flux linkages, we will calculate what is the distance between these two conductors and what is the radius of this conductor, and that relations we can simplify and we can able to get that the inductance per conductor is nothing but either individual conductors or it's because of both are similar conductors, we are going to consider that LA is equal to LB. Similarly, similar inductance is going to be developed in the conductor. So L is equal to 2 into 10 to the power of minus 7 ln d by r dash henries per meter. Here this equation is nothing but generally that whenever the current passing through the conductor, the amount of flux is going to be linked with this conductor. That the amount of flux linked with internally and externally of the conductor. So we have to calculate that what is the internal flux linkages and what is the external flux linkages. Both will be added together. You will get the total inductance of the conductor. So like that, that internal flux plus external flux, both the things we have added and finally have simplified. You are going to get this equation as 2 into 10 to the power of minus 7 ln d by r dash, where d is the distance between the two conductors, r dash is the fictitious radius of the conductor, actual r is the radius of the conductor, fictitious radius is nothing but 0.7788. This is the fictitious radius of the conductor. Then if you consider that this is the first single conductor, individually if we'll take, that is the inductance. For together, if you consider what is the total inductance, then the total inductance will be this inductor, this conductor inductance plus this conductor inductance. That means loop inductance. The loop inductance is nothing but LA plus LB. So twice of this value, you are going to get 4 into 10 to the power of minus 7 ln d by r dash henries per meter. So loop inductance is the total inductance of this entire conductor is nothing but 4 into 10 to the power of minus 7 into ln d by r dash. So like this, we can able to calculate the inductance of a two-wire line. Then the inductance of the three conductors which are symmetrically placed. Symmetrically placed means the distance between the two conductors is same and equally displaced. So this type of symmetric connection, then what will be the inductance? What will be the inductance? So that inductance can be calculated. Similarly, flux linkages divided by the amount of current passing through the conductor. So in what we are going to do is, this is the similar conductors and equally displaced. So individually we can able to calculate the inductance. That is, let us take the in the conductor A. Then what will be the inductance is lambda by IA. Actually, this is LA. It's a mistakenly has given it's lambda A. It is LA. So LA is nothing but lambda by IA. So this is equal to 2 into 10 to the power of minus 7 ln d by r dash henries per meter. So like this, we can able to calculate each conductor what is the inductance. Similarly, these two conductors also are identical conductors, so the same value of inductance will be there. So LB is once again the same and LC is also once again the same. So if we want to find out the total inductance, then this total inductance will be inductance of the three-phase line is equal to the two-wire line. So equal to that. Then unsymmetrical three-phase line. Unsymmetrical means the conductors will be displaced with a different distances. It's not equal to D. It is different from this distance is different from this distance. That's why unequal distances they have connected. It is not a symmetrical connection. It is unsymmetrical connection. So when the unsymmetrical connection is there, then you have to calculate what is the inductance of each conductor. So for that, what we have to calculate is, instead of calculating just simply like D, we are going to calculate what is the distance D and what is the other distances with the other conductor. So one is the D12. These are the geometrical distances between the three conductors, and this is known as a GMD, geometrical mean distance we are supposed to calculate. The geometrical mean distance is like this: 1/3, three conductors are there, 1/3 of the distances between the all conductors from one conductor to the other. So like this, we can calculate the geometrical mean distances, and this is the total inductance of the conductor A. And similarly, the inductance of the B and C also we can able to calculate. That is, again we can take it as a geometrical mean distance, and similarly by R dash. The values of inductance for the three phases are equalized by transpositions. And these conductors will be, because these are unsymmetrical three-phase line, and three-phase line means these three conductors can be transposed. This conductor may replace it with this conductor. This may be like this. It's a transposed condition. If we make a transposed condition, even then also the inductance will be calculated like this and value will be like this. That means here transposed means we can have suppose line length L is there. Every 1/3 of length, these three conductors will be changed its positions. 1/3 of the length of the line, all these three conductors will be changes its positions. Like this, it's a transposed. Transposed means A conductor becomes a position of C, or C conductor becomes a position of B, like that. So it is going to be transposed, means it changes their position. At the time also the inductance can be calculated like this. Then come to the inductance. Already means number of problems and the number of means the derivation of these equations already in the textbooks are available. So that's why I'm not giving much discussion on this derivation part. I have given only the equation part and how we are getting all this I am explained. And the next thing is once you know the resistance and then inductance, then the third one is the capacitance. What is the capacitance? Why the capacitance is occurred? The capacitance is mainly due to the electric field. Whenever the current charging conductor is there, then automatically electric field is going to be exhibited surrounding the conductor. Due to that, the capacitance is going to be the effect of capacitance will observe in the conductor. So due to that, the capacitance we supposed to calculate by the amount of charge which is supplied to this conductor divided by the amount of voltage gradient obtained across the conductor. So QA, the amount of charge which is given to the conductor divided by the voltage gradient from the A to the conductor B. So like this we can able to calculate. So CAB is nothing but QA by VAB. So this once again we can calculate QAB is capacitance between the conductors is nothing but similar to your inductance. We will calculate that pi into epsilon divided by Ln into d by r, Ln d by r, where d is the distance between the conductors and r is the radius of the each conductor. So CAB is referred to line capacitance, line to line capacitance. The capacitance between each conductor and point of zero potential N. Suppose potential N means neutral point is considered in between these capacitors, in between these two conductors. Then this capacitance also divided into two parts. One part is at C. Towards A side and one part is towards B side. That means between A and N, one capacitance capacitance effect will exhibit, and similarly between N and B there will be one more capacitance effect we can able to observe here. So similar, so when you are going to consider the neutral point, then what will be the capacitance between conductor to the neutral? So that is the Cn. Cn can be written as what is the amount of current passing through the conductor divided by, because the voltage is reduced. Previously voltage is VAB, because of neutral, the exactly middle of the line. So we are going to consider that half of VAB this side and this side. So like this we have taken half of VAB. So QA is nothing but similar that to pi E by Ln d by r, but here half is there, that so 2 will be in the numerator. So 2 pi E by Ln d by r farad per meter. So exactly the neutral capacitor, that the capacitance between each conductor and point of zero potential N is exactly twice the value of conductor, the value of capacitance between the conductors. So here we can write that Cn is equal to twice CAB, capacitance to neutral or capacitance to ground. Whatever, it is twice the value of capacitance between the conductors. Then similarly, the capacitance of three-phase overhead line here. So these conductors are placed equally and equal spacing between the conductors, and so whenever equal spacing between the conductors, then what is the capacitance of this conductor A is 2 pi epsilon naught divided by log A d by r. Then the distance between this, and when you are going to consider the neutral point, then that 2 will be existing. Here actually the capacitance of conductor with respect to neutral is 2, but without neutral this value is pi into epsilon by log E t by r. So this 2 is because of neutral connected. Then at neutral capacitance between the conductor and neutral, what is the capacitance is 2 times pi epsilon divided by log E d by r. Then unsymmetrical spacing, capacitance from conductor to neutral. Here also, if the symmetrical spacing, we are able to write that simply D. If it is unsymmetrical spacing, that means the D distances between the conductors, the conductors connected with different spacing, then at that time the D cannot be taken as directly. We can take that GMD, that is geometrical mean. With the neutral to the conductor to the neutral. If the neutral is not there, only conductor to the conductor, then these two will not be there. So pi epsilon by log E cubed root of D1, D2, D3 by R. Then capacitance of the two wire line. Sorry. This. Then generally the capacitance, whenever you are going to discuss about the capacitance, the earth will have much effect on the capacitance calculations. Why it is so is earth will be taken as a infinite potential conductor, like earth will be, earth we are considering as image conductors below the ground at a depth of height, and it is actually equipotential surface. Earth is a big potential surface. We are going to consider that a big potential surface. So because of that, the capacitance will have effect due to the presence of earth. Whatever the calculation of capacitance, if we do when the earth is existing, that calculations will not be correct, because earth we are going to consider as equipotential surface. Due to that, what will happen is that whatever the calculations we are going to do, all that calculations are not exactly the same as when the earth is existing. So when the earth is existing, then how we are going to consider is, when earth is existing, that to consider the effect of earth, we are considering image conductors below the ground at a depth equal to the height of the overhead conductor. If suppose overhead conductors are above is there, then below that ground level, the same height image conductors we are going to consider with the same height. Above the ground with opposite, but that conductor charge is opposite to the overhead conductor. So because of that, what will happen is the capacitance calculations will be modified. Previously, the capacitance between the conductors will be pi epsilon by L and D by R. But due to the presence of earth, image conductors are going to be assumed, considered. Because of that, we are going to calculate what is the effect of earth in the calculation of capacitance. That effect of earth will be taken like this: Ln into Hxy by Hxx. That is nothing but Hxy is the distance between the other conductor. Hxs is similar conductor. X conductor is this is the earth. Let us take the conductor X is here. Then the image conductor will be X dash with the same height and and if the conductor X is a positive charge, X dash will be a negative charge. Like this, the earth plane will be like this, and image conductors will be below the ground level, below the earth surface, and charge of that conductor is always negative charge of the overhead conductors. If we are going to consider like this, then the effect of these conductors, the negative charge effect also we have to consider while calculating the capacitance calculations. So the capacitance will be calculated with the pi epsilon by L and dr minus the effect of this negative potential, that is Ln Hxy by Hxx. This will be the capacitance of the conductors when earth is present. When the earth is not there, this value becomes 0. Then neutral capacitance is nothing but 2 pi. Already we know that twice of the conductor capacitance, so twice of that same value. If conductors are very much above the ground, then very much above the ground means this height is very high, then the difference between these two heights will approximately considered as equal. When these two are approximately equal, what will happen is this becomes 1. So 1 will be there. It's a numerical value of amount will be taken as in the denominator, and finally this value will get reduced. So with the effect of earth, the capacitance increases. With the effect of earth, the capacitance increases, because here it is a negative part. So when the far away, the conductors are too high, then the image conductors also with the same height will be there. So hxs and hxy will be assumed to be equal. At that time, this value will be equal to ln of 1, and this total value will reduces. So capacitance value increases. The effect of earth will, what will happen is the capacitance value is going to be increases. Then in all the calculations we have not discussed about what is the type of conductor. Simply we are taking that conductor is there, and with the conductor are displaced some distance d, and we are able to calculate the inductance and capacitance values. But inductance and capacitance values for if the conductors are different type of conductors like bundled conductors, then what will be the inductance and capacitance? For the bundled conductors, the inductance will be simply you cannot take the distance between the conductors, and simply cannot take the radius of the conductor. Now bundled conductors means more than one conductor they have connected per each phase. So because of that, we have to calculate the geometric mean distance and the geometric mean radius. So we are going to get the inductance of a bundle conductor is nothing but 2 into 10 to the power of -7 ln GMD by GMR. Actually this is Henrys per meter, not for a farad per meter. It's a Henrys per meter. You can change the means. You can observe this Henrys per meter, and the capacitance is 2 pi epsilon divided by ln GMD by GMR. Here also the same procedure. GMD means it's not simply D. We need to calculate geometrical mean distance, and simply R cannot be taken here as the geometrical mean radius. You have to consider if the conductors are bundled conductors. In a previous case, the conductors we are not mentioning that the type of conductors. Here only conductor is there. Conductors are displaced, asymmetrical spacing, unsymmetrical spacing, like that we have taken, and we have calculated the values of L and C. But if the conductors are bundled means you know very well that more than one conductor they have connected bunched. They have connected as a bunch per phase. So at that time, bunched conductors means we have to calculate geometrical mean distance. So like this we can able to calculate the inductance and capacitance. So here a simple summarizing of the information regarding the resistance, inductance and capacitance with the length, distance and radius and other things. So first we will consider that length. So for the resistance, if the length increases, resistance increases, no doubt. It's a rho times L by A, so it is increases. Then the inductance. Inductance also increases because the length is radius of the inductance is Henrys per meter. We are considering per meter. We are calculating all the calculations. If the meter, that means the length of the conductor increases, then the inductor value also increases. That is the meaning here. Then the capacitance also farad per meter we are considering. So farad per meter means this, then automatically the capacitance value is also increases. Then the inductance increases, the reactance value increases, capacitance increases, capacitor reactance is decreases because 1 over omega C. Because of that, this decreases. But XL is nothing but omega L. So this increases, automatically this will increases. So like this, the length increases, resistance increases, inductance increases, capacitance increases. That is the summarized meaning of all the parameters in a transmission line. Then distance of separation increases. Distance of separation means conductor to conductor. If the distance increases, what will happen? The resistance will not have any relationship with the distance, so no relation. But inductance, you can see that the inductance is a numerator value, distance will be there. So inductance distance, this distance GMD increases, L increases, so length increases. Then automatically omega L increases, and the capacitance, you can see that it is in the denominator. This increases, automatically capacitance increases. So this GMD value, the distance increases, this increases, then this decreases, no doubt in that, because it's an inverse relationship, so we can say that it is decreases. When this capacitance decreases, capacitive reactance is going to be increases because of 1 over omega c. Then radius of conductor increases. The radius increases, then what will happen? Resistance. Resistance radius means rho times L by A. A is modified. When A is modified, automatically resistance is also, because inverse proportional, radius increases, automatically resistance decreases, and the length, it's inductance. Inductance is will have the inverse relationship, so automatically the length increases, inductance decreases, and that reactance, inductive reactance is directly proportional, so it is decreases. But capacitance, what will happen? It is inverse relationship with the with the radius of the conductor. So when the radius of the conductor increases, this capacitance increases. So with that, the capacitance increases and omega c is decreases. Then symmetrical spacing. Symmetrical spacing means between the conductors, symmetrically spaced. The three phases how the conductors are displaced. So three phases how the conductors are displaced means that resistance will not have any relation with that symmetrical distance, and length this inductance is decreases, because you know very well that GMD, GMR values will be modified, then automatically this decreases, and capacitance increases, inverse relationship. Then unsymmetrical spacing, resistance will not have any relation, but inductance will have unsymmetrical spacing means this distance, geometric mean distance will vary, then automatically the inductance increases, and in the capacitance this vary, then automatically the capacitance decreases. Effect of earth taken into account. Effect of earth means the resistance will not have any effect. Inductance also will not have any effect, because earth no way affects the inductance. So inductive reactance will not have any effect, but the capacitor, because of the earth, the capacitance increases and the capacitive reactance decreases. Then height of the conductor increases. Height of the conductor means if the just now I have explained that height of the conductor increases, then resistance and inductance will not have any relationship, but capacitance will be decreases, because already I told that Hxx and Hxy will. If you remember all this, so depends upon the length, distance, and radius, as well as symmetrical distance, spacing distance, and unsymmetrical spacing distance, effect of earth, and height of the conductor. Radius, and the remaining will have no relation, but inductance will have inductance will depends upon length, distance, radius, symmetrical spacing, unsymmetrical spacing, and only the effect of earth and height of the conductor. Summarization. So if any question asks, if you remember this, automatically you can able to answer the question directly. So you can remember, or you can analyze this here it is. Now I have given the table. Increase in diameter of the conductor, increase in spacing between the phase conductors, increase in load current carried by the conductors. The inductance of the transmission line increases with, what is the answer? Mainly increase in spacing between the phase conductors. For the example, D is space between the conductors, R dash is the effective radius of the conductor. So L inductance is directly proportional to logarithmic value of D. So R dash is nothing but a almost constant value. So it's a directly proportional. So when it is directly proportional, when the distance increases, automatically this will be the inductance is increases. So that is the meaning in this. The next question. The insulation resistance of the cable of length 10 kilometers is 1 mega ohm. For a length of 100 kilometers of same cable, the insulation resistance will be. So the insulation resistance of the cable length. So here resistance calculations you have to carry it out. The insulation resistance of the cable length is 10 kilometers is 1. Insulation resistance is 1 mega ohm, length is 10 kilometers. If it is 100 kilometers, then what will be the insulation resistance? That is the question they have asked. So insulation resistance of the cable, actually this formula is in cables, we will derive this formula directly. I have taken this formula. So R is equal to rho times 2 by L, Ln R by R. This is the insulation resistance. But here R is actually, this is the resistance, this is the cable radius, like this R is the core radius. So that the insulation resistance is inversely proportional to the length of the cable. So R is inversely proportional to 1 by L. So this relation can be written as R2 by R1 is equal to L1 by L2. Then R2 is equal to L1 by L2 into R1, L1 by L2 into R1. Then R2 is equal to simplification, we will get that 0.1 megavolts. If the length of the cable increases, the resistance of the cable is reduced. That is the meaning here. Then another problem is a three-phase overhead transmission line has its conductors horizontally spaced with spacing between adjacent conductors equal to D. If now conductors of the line are arranged to form an equilateral triangle of sides equal to D, then so this is the another problem. A three-phase overhead transmission line has its conductors horizontally spaced with spacing between adjacent conductors. Now conductors of the line rearranged. That means it's a transposition, like transposing the conductors. When the transposing the conductors, then what will be the what will be the capacitance and inductance? That is the meaning. If transposition of conductors is taking place, then what will be the capacitance and inductance? So they have given the option is average capacitance and inductance will increase, average capacitance will increase and inductance will increase, average capacitance will increase and inductance will decrease, surge impedance loading of the line increases. For that, what is the answer? The answer is actually when the conductors are horizontally spaced, then the value is 0.2 Ln GMD by GMR. Capacitance is nothing but 2 pi epsilon Ln into GMD by R. But in this value is GMD is nothing but cube root of root 2 and 1.26 GMR. This is the first horizontally placed. When this is transposed with the equilateral triangle, then what will be the GMD and the GMR? GMD is directly equal to D, equilateral triangle means equal spacing. So GMD is nothing but D. Then GMR is nothing but 0.7788 R. So if you find out that inductance is directly proportional to Ln GMT, capacitor is inversely proportional to 1 by Ln GMT. This is direct relationship, this is inverse relationship. From this case 1 and case 2, inductance what exactly is? Inductance decreases and capacitance increases. This value is here decreases, this value it is decreases means this value is increases. So like this, from the analyzation of these two diagrams, we can know that the inductance decreases and capacitance increases. If conductor is placed horizontally and it is transposed into equilateral triangle. Then another is two conductors of 10 kilometers long, single phase, two wire line are separated by a distance of 1.5 meters. The diameter of each conductor is 1 centimeter. If the conductors are of copper, the inductance of the circuit is. They ask you to find out that what is the value of inductance if the conductor's length is 10 kilometers, two wire line is they have used with a separation of 1.5 meters, and each conductor diameter is 1 centimeter, and the conductor is made up of copper. So if the single phase circuit with copper conductors, then the inductance is nothing but LAB. Is a they have given two wire line, that means two conductors are separated with a distance of D. So that is the formula you have to use. So the total inductance is nothing but LA plus LB, loop inductance. So loop inductance is nothing but 2 into 0.2 ln D by R dash. So you can substitute that values. You are going to get loop inductance is 2.38. But actually they have given the length also. This is actually Henrys per kilometer. You are getting its this value is to 10 to the power of minus 7, that will be converted into millihenries per kilometers. So this value you are going to get, it is a millihenries per kilometers, but actually they have given 10 kilometers long. 10 kilometers long means this value will be modified like 2.38 into 10 millihenries, so 23.8 millihenries. So here actually maybe you will get the doubt, it is 0.2 only they have written, it is why it is not giving 2 into 10 to the power of minus 7, but actually 2 into 10 to the power of minus 7 or 2 into 2 it is 4, 4 into 10 to the power of minus 7 is henries per meter, but here they have considered is 0.4 in terms of millihenries per kilometer. The 10 to the power of minus 7 they have divided in terms of millihenries per kilometer. That values 10 to the power of minus 7 they have modified and they have taken the change of units. So LAB is equal to 2.38 millihenries per kilometer. Then for 100, then for a 10 kilometers long, that means the conductor size is 10 kilometers. Whatever the calculated per kilometer inductance multiplied with 10, you are going to get the total inductance for 10 kilometers length. So LAB is equal to 23.8 millihenries. Then another problem is, they have asked in GATE 2002, that is, consider a long two-wire line composed of solid round conductors. The radius of both conductors is 0.25 centimeters and the distance between their centers is 1 meter. If this distance is doubled, then the inductance per unit length. So you can see that it is once again two-wire line, and the solid conductors, they are round conductors they have given. Radius they have given for both the conductors is same, and distance between is 1 meter each. Then if the distance is doubled, then the inductance, what will happen? Distance D is double, then inductance will be double, half increases but does not double. So what will be the answer? So already you know the equation, 0.2 ln D by R dash. Then D they have given as 1. D has given as 1 meter, so they have taken as 1, and R they have taken as 0.25. So inductance per phase is nothing but they have calculated in terms of millihenries per kilometer. If the distance between the conductors is doubled, then D becomes doubled. Then they have calculated the inductance. If you observe that 1 meter distance, what is the value of inductance? If 2 meters distance, what is the value of inductance? Then what will be the inductance? The inductance, if you observe, it is not exactly doubled, only increases. The table also I have told the distance increases, the inductance increases. So only increases, but not exactly the double the length of the line. It is not directly proportional. So the length of the conductor increases, then the inductance increases, not exactly double. So that is the meaning in this. Hence inductance per increases but not doubles. That is the answer. Then the horizontally spaced conductors of a single phase line operating at 50 Hz are having outside diameter of 1.6 centimeters and the spacing between centers of conductors is 6 meters. They have taken the again single phase line operating 50 Hz and the outside diameter is 1.6 and the spacing between the centers of the conductor D is 6 meters. The permittivity of free space is epsilon they have given. The capacitance to ground per kilometer of each line they have calculated. So capacitor to ground means that is the value of capacitance to neutral like CN. CAN or CN, whatever maybe it is, they asked you to find out. So that is already you know very well that the formula is 2 pi epsilon by L and D by R. Here depends upon the value of material, you are going to get epsilon R also in the equation. So you can substitute here epsilon R. They have not mentioned that epsilon R. So epsilon R will be considered as 1. So directly you can take the 2 pi epsilon by L and D by R. D by R. So they can substitute the values of D and R. Then you can simplify, you will get the values of CAN. So CAN in farad per kilometers. Farad per kilometers they obtained with the values of 0.8 and 6. Then the another problem is a single phase transmission line has two conductors, each of 10 mm radius. So conductor's radius as given. These are fixed at a center to center distance of 1 meter in a horizontal line. These are fixed at a center to center distance. That means it's a distance between these two conductors they have given as 1 meter. This is now converted to three-phase transmission line by introducing a third conductor of same radius. That means previously they have used the two conductors. Now they are going for a three conductors with a three-phase transmission. This conductor is fixed at an equal distance D from the two single phase conductors. That means that the incoming conductor is exactly connected to these two existing conductors with equal spacing. Equal spacing, that means it is nothing but a right angle, equilateral triangle. So the three phase line is fully transposed with the symmetrical, that means symmetrical spacing like fully transposed. Then the positive sequence inductance per phase of the three system is to be 5% more than that of the inductance per conductor of the single phase system. They have given that for the three phase system the inductance is increases by 5% than the two single phase system. Then what is the distance in meters? What is the distance D? Actually they have taken that radius as given. Initially two conductors have connected like this. The radius is 10 mm and the distance is some D. Actually they have not mentioned, it's 1 meter. The distance between them is 1 meter. So it is a 1 meter. It's, everything is converted into millimeters. So this also 1 meter means 1000 millimeters and radius is 10 millimeters. Previously the connection was like this. When one more conductor is added here with equal spacing between these two conductors, so it becomes a equilateral triangle and the distance is like this. So what will be the distance? What will be the distance in meters? What will be the distance? The conductor is fixed at an equal distance D from the two single phase conductor. This distance, this distance. What will be this two equal distance? They have connected this conductor. So what is the distance D of this two conductors are this conductor? This is the equal distance. So either this distance or this distance you are supposed to calculate. So what will be the value? For that, what is the hint they have given? Whenever you will calculate for this inductance, that value is some value. And when you are going to calculate inductance, that value of inductance is 5% more than this value of inductance. So 1.05 is the more. 5% means actually 100% will be the value of inductance here. Means if this is the value 5% more means 100 plus 5. So 1.05. 1.05 is the increase in inductance when with the single phase. That three phase inductance will be 5% more than the single phase. So this equation we can able to write it, and with this L single phase we can able to calculate. It is point that equation directly we know that 0.2 into L and D by R. d by r, and this also we can able to calculate because it's a triangle equally, that means a symmetrical spacing, like not symmetrical, at least it is unsymmetrical, but even then these two distances are equal, and but this distance is 1000 mm. So with this uh, spacing, similar spacing conductor, so we can able to directly calculate 0.2 ln. This is nothing but GMD. They have calculated GMD and then radius of that. So r dash. Then this equation will be simplified. So once you will get the simplification, then the value of distance d, here what is the value of distance d can be calculated, and the value becomes 1.438 meters. 1.438 meters. So this is in, with these two conductors may be some distance, but this to this and this to this is equal spacing. But this spacing is not exactly same as this thing. So it is not a equilateral triangle. It is different, but it is triangle in condition and spacing differently. Three conductors are three conductors are here. You can see that conductor is fixed with the three-phase line converted into by introducing third conductor. So we have added some conductor. This type of connection will have the inductance, like by considering that GMD of this type of connection. Instead of D, we will consider that GMD. So once you will calculate the GMD, then we can able to substitute this equation. With this equation, we can able to get the value of D. This is simple problem, but you have to understand. Then a 6.6 kV 50 Hz single core lead sheathed cable has the following data. Conductor diameter, it is 1.5 centimeters. Length is 4 kilometers. Internal diameter of the sheath is 3 centimeters. Resistivity of insulation, it is they have given is 1.3 into 10 to the power of 12 ohm meter. Relative permittivity of insulation is 3.5. Calculate insulation resistance, the capacitance, maximum, the max electric strength in the insulation. This is actually cable problem, but even then it's a cables already is there in your syllabus, so this is a cable problem, but anyway is there. We can discuss that cable. Insulation resistance, already we have seen the equation. What is the insulation resistance? Is R is equal to rho times 2 pi L into L and R by R. You can just substitute all the values, you can get that insulation resistance. Then similarly capacitance, is nothing but epsilon by 18 ln R by R. This is the insulation, that capacitance of the cable. So directly you can substitute, you can get that. And next is electrical stress. The max electrical strength in the insulation. That value is nothing but Z max is equal to V by R into ln R by R. This is the electric stress. Directly you can substitute, you can get the values. This is actually cable problem, not the line parameters problem. But anyway, all these equations are known to you. Directly you can substitute and you can be able to get the values. Then the insulation level of 400 kV EHV overhead transmission line is needed on the basis of this is needed maybe. The insulation level of 400 kV EHV overhead transmission line is needed on the basis of lighting over voltage, switching over voltage, corona inception voltage, radio and TV interference. 400 kV EHV overhead transmission line, how you are the insulation level of that, how will you consider is, it's a completely theoretical question. That is a insulation level is nothing but to withstand the fault on the transmission line. How or whatever the faults are, what is the abnormal values of current or voltages are there to withstand, what is the value of insulation you are supposed to carry out with this transmission line. That is the meaning in this. So transmission level of voltage, insulation level of EHV overhead line is mainly depends upon the switching over voltage. Switching over voltage is nothing but one of the fault. or lightning over. This is also a fault only, but this is switching operating condition. At the time of switching, what type of insulation level we have to use. Lighting is it's like abnormal condition which is arise due to some other means. But switching is frequent operation of transmission line. Then in any transmission line, lightning over voltages are more severe compared to switching over voltages. The lightning voltages are external voltages, hence insulation is provided for switching. Insulation, the normal operating at the time, normal operating conditions of the line, that is switching operations. But this is lightning is once again the faulted condition, but it is external voltages. It is not exactly internal requirement. A long wire composed of smooth round conductor runs above parallel to the ground. A long wire composed of smooth round conductor runs above parallel to the ground. Okay. Assume to be large conductor. So ground is nothing but they are assuming that it's just like equal to earth. Large ground conducting plane. A high voltage exists between the conductor and the ground. The maximum electric stress occurs at. So this ground potential is very large. They are considering the large conducting plane like earth you can consider. At that time, a high voltage exists between the conductors and the ground. High voltages exist, then what is the maximum electric stress occurs? What is the maximum electric stress? So the upper surface of the conductor, the lower surface of the conductor, the ground surface midway between the conductor and ground. So how we will answer this is the lower surface of the conductor they are giving. The lower surface of that means it's a large potential is below the means earth, the earth where that ground potential is large potential, so always the conductor below that will have a large stress, electric stress. That's why they have taken as lower surface of the conductor. The related voltage of a three-phase power system is given as how will you measure the voltage of a three-phase power system? Either RMS phase voltage, peak phase voltage, line to line RMS line to line voltage, peak line to line voltage. Always measured is always RMS, and also it is a transmission line. So we are going to consider that line to line voltages, not the phase voltages. So line to line RMS voltage is the correct answer. Always measurement will be done with the RMS values. And also due to the transmission line, generally transmission line means phase to line to line we are going to consider instead of phase to phase. Then bundled conductors are mainly used in high voltage overhead transmission lines too. Bundled conductors, what is the purpose of usage of bundled conductor? To reduce the corona. So that is the answer. Directly we can give reduce transmission line losses, increases mechanical strength of the line, reduce corona, reduce corona. For bundled conductors, increase in self GMD will be predominant compared to decrease in self GMR. Decrease in self GMR. So hence electric field intensity at surface of each conductor will be reduced. Hence the corona loss will be reduced because chances for ionization of air are reduced. Generally, electric field intensity at surface of each conductor will be reduced because GMD increases when compared to the GMD and the GMR. GMR is always more effective than GMR value. Because of that, conductor electric field intensity of the surface reduces, corona loss will be reduced, that ionization effect also will reduce. For equilateral spacing of conductors of an untransposed three-phase line, we have equilateral spacing of conductors of untransposed, symmetrical spacing. Balanced receiving end voltage and no communication interference. Unbalanced receiving end voltage and no communication interference. Balanced receiving end voltage and communication interference. Unbalanced receiving end voltage and communication interference. So for that, what is the answer is? No doubt it is equilateral spacing is symmetrical, and untransposed means it's no transpose. So for the transmission line with equilateral spacing of conductors, inductance per phase is equal, and inductance per phase of each conductor is equal. So inductance is same, then current is going to be same. Means when the inductance is same, lambda by I is going to be the same. When lambda is going to, the flux is going to the same, then the voltage is also will be the same. So hence no communication interference, and also the receiving end voltages are balanced. That is the meaning. So the answer will be balanced receiving end voltage and no communication interference. For a single phase overhead line having solid copper conductors of diameter 1 centimeter, space is 60 centimeters between centers, the inductance in millihenries per kilometer is. So, how will you calculate? This is the diagram what they have given. Overhead line having solid copper conductors of diameter 1 and spaced between 60 centimeters. Then what is the inductance? Directly you can able to calculate that internal plus external. That simplification you can get it half of 10 to the power of minus 7 into 2 into 10 to the power of 7 L and D by. After simplification with millihenries per kilometer they are taking. That after simplification you are going to get 0.05 plus 0.2 into Ln 60 by 0.5 millihenries per kilometer. So that is the answer. So this will be the answer. They have given in millihenries per kilometer, this will be the answer. If it is henries per meter, then this may be the answer. This may be the answer. A composite, yeah. So all these problems already you have seen, and so almost all gate, whatever the problems I have obtained in gate, I have shown here and I have explained according to the theory, and analyzation. But I want to give you some of problems for homework. So let us do these problems. It's a direct, simple solution, simple problems. These are you can able to calculate and you can give me the solutions for tomorrow's class. This is the one problem. A composite conductor consists of 3 conductors of radius r. The conductors are arranged as shown below. The conductor radius is like this, and the distance between these conductors is 3r. Geometric mean radius of the composite conductors is kr. Actually, kr means it's a 3r. Kr. The value of k is geometric mean distance you have to calculate. That is, here it is the distance between the conductors 3r has given. Here maybe 3r, here also 3r. What is the geometric mean distance is cubed root of 3r d1, d2, d3. Cubed root of d1, d2, d3 you can calculate and you can simplify so that the value of that is equal to kr. Then you can find out the value of k. So it's a very simple problem. You can simplify and you can give it to me for the next class. Then this is another problem. Consider an overhead transmission line with a 3-phase 50 Hz balanced system with conductors located at the vertices of an equilateral triangle of length DAB, DBC, DCA equal to 1 meter. Equally, all 3 distances are equal to 1. The resistance of the conductors are neglected. Resistance is neglected. The geometric mean radius of each conductor is 0.01. That means R dash they have given directly. Neglect the effect of ground. Ground also they have neglected. Then the magnitude of positive sequence resistance, reactance in ohm per kilometer rounded up to 3 decimal places is what? They have given that. First, what you have to do, it's a very direct problem. You have to find out the inductance because it's a equilateral spacing. So directly you can calculate the inductance of the equilateral triangle. This balanced system, overhead balanced system of overhead transmission line. 4 into 10 to the power of minus 7. 2 into 10 to the power of minus 7 into L and D by R. L and D by R because equal spacing and They have given GMR is 0.01, or GMR already has given. You can able to calculate GMD, L and GMD by GMR. You will get that L. Inductance you can calculate. Once you know the inductance, they have given that 50 Hz balance and system frequency has given. They asked you to find out that reactance is nothing but omega into L, 2 pi f L. 2 pi f L, f already given, 2 and pi are the constants. So directly 2 pi f L you can able to calculate by the formula. So 2 pi f L directly you can calculate, and you can give the value in terms of ohms per kilometer. So that is another problem I am giving to you for assignment. So you can do it. So this is the line parameters of the transmission line. How the resistance, inductance, and other things are affected with the value of the value of length of the conductor, diameter of the conductor, and spacing of the conductor, and all. Now I am going to move on to the another presentation. That is another presentation is another one is performance of the models and performance of transmission lines. So models and performance of transmission lines. The models and performance of the transmission line is this is that outline presentation is generally types of introduction, types of transmission lines, depends upon the length. We are going to divide in types of transmission lines, and what are the effects of skin effect, effect, efferent effect, surge impedance, and then again gate questions, and further we can give the some problems to work out. Then introduction. The important consideration in the operation of transmission line are voltage drop, power loss, and efficiency. Main important thing, the performance of the transmission line is only obtained by calculating the voltage drop, power loss, efficiency. These are the efficiency. The voltage drop is nothing but regulation, and the power loss is nothing but I squared R loss, and the efficiency is nothing but output by input. So these three values, if you calculate, we can easily identify that the performance of the system. So what is the performance of the transmission line? These three values will be calculated again, or will be again depends upon the parameters of the transmission. That parameters of the transmission already I given that it's resistance, inductance, and capacitance, and the conductance it is. So what is the effect of the resistance effect is no doubt it is one is the voltage drop, and other one is the power loss. Voltage drop is nothing but I into R, power loss is nothing but I squared R. Then what is the effect of inductance? Effect of inductance is no doubt it is voltage drop, that is 2 pi FL, that is omega L. Then effect of capacitance, that is nothing but charging current V by XC. So once again this also causes the voltage drop, that is the current reduction, that is charging currents. So V into 2 pi FC. Then effect of G, that is conductance. It is due to leakage current. It is predominant only during bad weather conditions. So generally this conductance effect will be neglected. Bad weather conditions only this leakage current will have much effect. So that's why this effect is not much predominant in the performance of the transmission line. If then overhead lines, generally when the reactance effect is more and when the capacitive effects is more is in overhead lines, the reactance, that is inductance values, the reactance effects are more. In underground cables, reactance effects are small and capacitive effects are more. That means in overhead line, inductance will give more effect than underground cable. But underground cables, the capacitance is more effect. The capacitance will have more effect on the underground cables than inductance. That is the meaning here. Then what is the performance? Already I told that efficiency. So efficiency is nothing but power delivered at the receiving end by power sent from the sending end into 100. That is output power divided by the input power. Then this once again how we are going to calculate is power sent from the sending end is nothing but power delivered at the receiving end plus losses. That losses, if you add it to the output power, we will get the input power. So power delivered at the receiving end divided by power delivered at the receiving end plus losses into 100 will be the efficiency. Then the end of the line where load is connected, generally receiving end is nothing but at where the load is connected, where the source is connected, that is the sending end. We are going to define that receiving end and sending end is, receiving end is nothing but the load connected point, sending end is nothing but supply connected point. Then the regulation of a line is defined as the change in the receiving end voltage expressed in percent of full load voltage from no load to full load. When the load is keeping the sending end voltage and frequency constant. When the load is applied, what is the change in voltage from no load condition to the full load condition with respect to the no load voltage is nothing but a regulation. So at that time we are going to maintain the frequency constant. So what is the mathematically how we will express percentage regulation is nothing but VR dash minus VR by VR into 100. Where VR dash is the receiving end voltage under no load condition and VR is the in voltage under full load condition divided by VR. So full load condition VR dash minus VR divided by VR into 100. Then this another important, and this is the main important thing you have to remember why we are going to consider this. Electrical power is being transmitted over the overhead lines is at approximately the speed of light. The transmission power is, how it is transmitted is how the speed of light will transmit. Similar to that, the power is going to be transmitted over the transmission line. So how we are going to, what is the one full cycle of voltage and current on the line? Transmission of one voltage, one full cycle of voltage or current on the transmission line is nothing but the length of the line is nothing but how we are going to calculate is F into lambda is equal to V. Where F is the frequency of supply, lambda is the wavelength, that is length of the line in this case, and V is the velocity of the wave, that is velocity of light. The velocity of light, velocity of the wave. So here how the power transmitted is, which is similar to the speed of light. How the speed of light will vary is nothing but F into lambda into V, where V is the velocity of the light and lambda is the wavelength and F is the frequency. Same equation will be holds good for power transmission in transmission system. That is the meaning here. So for example, F is equal to 50 Hz, B is equal to 3 into 10 to the power of 8 meters per second is the velocity. So lambda, that wavelength, the length of the conductor, or how much length of the line we have to use is nothing but V by F. V by F is nothing but it's the speed of that divided by the frequency, number of cycles. So this, if you get that, the length of the line is nothing but 6,000 kilometers for one cycle of operation with the speed of this. We will get that 6,000 kilometers length we supposed to add it. So 6,000 kilometers, one half cycle, if you want move that voltage or current wants to complete one complete cycle, the length of the transmission line needs is 6,000 kilometers. 3,000 kilometers means only one half cycle is going to be completed. Voltage distribution of 50 Hz supply is like this. So this is very important. We can say in order to complete one complete cycle of sinusoidal wave takes 6,000 kilometers physical distance of transmission line. Physical distance of transmission line. So now you know that what is the how the voltage will take one cycle of operation, how much length it will take. So depends upon that. Here once again, based on that length, the transmission lines can be classified. So if the length of the line is less than 80 kilometers, then we are going to consider as short transmission line. If the length is greater than 80 kilometers and less than 160 kilometers, then that will be considered as medium transmission line. If the length of the line is greater than 160 kilometers, then we can consider it as a long transmission line. So we can classify this depends upon the length. So each and every line will find out what is the resistance, inductance, capacitance effects. So the lines up to 80 kilometers are short transmission lines where the effect of shunt capacitance is neglected. The length, because the length is short, the capacitance effect is neglected. So only inductance and reactance will be there. So the short transmission line equivalent circuit will be drawn like this. So sending end voltage and current, receiving end voltage and current, and the amount of impedance or the amount of resistance and reactance of that transmission line will be represented as R plus Jx. That capacitance value is negligible. Then what is the vector diagram of that? Vector diagram is receiving end quantities are known to us. The sending end quantities can be calculated like this. Initially, we are going to consider that VR is the reference or IR is the reference, whichever you want to take it as that we can take. But I will take that VR is the reference. Then with the VR, IR is a phase lag by phi r and phase lag by phi r. Then IR, the resistance drop is always in phase with the amount of receiving current. So in phase we can write it, and the amount of reactance drop is exactly perpendicular to the receiving end current. So I will take that this as a perpendicular. If we join this from this point to this point, from 0 point to this point, then that sending end voltage we can able to get it. That equation directly you can write it from this also. From this also we can write Vs is equal to Vr plus drop across this R plus Vx. So similarly from the vector diagram we can write that Vs cos phi s is equal to Vr cos phi r plus Ir into R. Vs sin phi s is equal to Vr sin phi r plus Irx. Why we are considering that cos x sin x is because it's a vector quantities and phasor quantities. We have taken that real part separately, reactive part separately. So Vs cos phi s plus J times Vs sin phi s is equal to Vr cos phi r plus, actually Vs at an angle of phi s is equal to Vr at an angle of phi r plus R plus Jx into Ir, that they have divided like this. Then the percentage regulation is nothing but, already we have explained that the drop in voltage divided by the full load voltage is nothing but percentage regulation. So regulation per unit is nothing but we can simplify this also. Vr at an angle of phi r and Vr dash at an angle of phi r dash we can take, and we can simplify this equation. We are going to get in terms of cos and sin. Vr cos phi r plus Vx sin phi r, we are going to get it, where Vr, Vx are per unit values of resistance and reactance of the line. Vr is nothing but I into R by Vr, Ir by V. Vx is nothing but Ix by V. So like this we are going to get some per unit values of resistance and per unit values of the reactance. A 4-terminal passive network of voltage and current on the receiving end and sending end are related by the following relations. So we are going to consider that short transmission line will be represented as a simple two-port network, because two-port network means the receiving end is there, sending end is there, receiving end is there, two ends are there, two ports we can consider, and the two-port parameters like sending end voltage and sending end current, and receiving end voltage and receiving end current, and intermediate, that impedance network will be represented as transmission line, just like it's a two-port network. So how we are going to write equivalent parameters for two-port network? So Vs is equal to A times Vr plus B times Ir. Is is nothing but C times Vr plus D times Ir. This is the ABCD parameters for this network. So where A is nothing but Vs by Vr, B is nothing but Vs by Ir, and C is nothing but Is by Vr, and D is nothing but Is by Ir. So the same relationship here we have written. This means that A is the voltage impressed at the sending end per volt at the receiving end when the receiving end is open. When the receiving end is open, then what is the sending end voltage with respect to the receiving end voltage? Is nothing but A, and this value A is it's a ratio of voltages, so there is no dimension for A, and it is voltage gain. It's nothing but voltage gain. B is the voltage impressed at the sending end to have 1 ampere at the short circuited receiving end. This is known as transfer impedance in the network theory. So we are going to consider that B is equal to Vs by AR, where VR is equal to 0, where VR is equal to 0. So Vs by AR, it is a ratio of impedance, Vs sending end voltage divided by the receiving end current at the when receiving end is short circuited. This is known as transfer impedance. Then C is nothing but Is by VR when the receiving end is open circuited, and this is nothing but a admittance, equivalent of admittance. That is, we can write that sending end current divided by the receiving end voltage. It's a dimension of the unit is dimension of admittance. And D is again, it's a ratio of currents when the receiving end is short circuited. When the receiving end is short circuited, then D is nothing but ratio of sending end current to the receiving end current. It is nothing but a current ratio, and this D is a dimensionless quantity. Then the sending end voltage and current can be written from the equivalent network as Vs is equal to VR plus IRZ, Is is equal to IR. So the constants are here from the circuit. From this circuit, they are writing the equivalent circuit. Vs is equal to Is. Here they are writing that Vs is equal to VR plus IR into Z. Is is nothing but IR. So from this will be compared with the ABCD parameter 2-port equations. So A is equal to 1, B is equal to Z, C is equal to 0, D is equal to 1. So these ABCD parameters for the short transmission line is like this. Then determine the sending end voltage using the relation Vs is equal to A plus B into IR, and to determine VR is nothing but no load voltage at the receiving end is VR dash is equal to Vs by A when IR is equal to 0. From this equation, they are writing that IR is equal to 0, then VR is equal to Vs by A. From the obtained relations, we can write percentage regulation is nothing but Vs by A minus VR divided by VR into 100. Then regulation can be the difference of voltage from no load to full load. That is the meaning in this. To determine percentage of efficiency of transmission, the following relation is made use of. Power delivered at the receiving end is P, and power delivered at the receiving end is P plus what is the losses is because it's a 3-phase transmission system, 3 times I squared R. R is the resistance per phase of the line. So 3 times IR squared R. So this is the efficiency of the short transmission line. Then we will consider the medium transmission line. In this medium transmission line, 80 kilometers, 160 kilometers. Between that, we are classifying as a medium transmission line. It has been mentioned shunt capacitance is either assumed because it is that capacitance cannot be neglected because the length of the line is higher than the short transmission line. Because of that, the capacitance effect will be there. But here the capacitance, what we are going to do is we are going to consider in 2 different fashions. One is the middle of the transmission line. We are going to consider concentrated. The shunt capacitance is concentrated at middle of the line. That is one type of connection. Another type of connection is half of the total capacitance is concentrated at each end of the line. So like this, we are going to consider this capacitance. One is at middle, other one is at the ends of the both ends half of the capacitance. So like this, we are going to consider. When you are going to consider these 2 different types, that names they are given as one is in the middle of the line, that will be considered as it looks like say a T connection. So they are considered as a nominal T, and at the edges, at the ends, they have connected half of the capacitance. It looks like a pi connection. So they have taken as a nominal pi. So nominal T, in this method, the whole line capacitance is assumed to be concentrated at the middle point of the line, and half of the line resistance and reactances are lumped at either side of it. In this connection, in the nominal T connection, the capacitance is concentrated at the middle of the line. So because of this middle, that reactance and resistance will be connected half at the one end and half at the other end. So like this type of connection, this is known as nominal T connection. Therefore, this arrangement, full charging current flows over the half of the line. Full charging current flows over half of the line. in figure 1 phase of 3-phase line is shown as it is advantageous to work in phase instead of line to line balance. Phase in because of it is a balanced circuit, we are going to consider phase wise calculations. It's only single phase representation. We are single phase balanced circuit we are showing for the medium transmission line like this. Then the vector diagram for a lagging power factors, we can see that receiving in currents as the reference vector. Receiving currents they are taking as reference vectors as calculations become relatively easier as compared to taking VR as the reference. So anything you can take, okay, they are considering that IR is the reference. So IR they have taken as a reference. So VR is always, IR is always lags with the voltage of VR. So VR leads. So VR can be written like this. Here the value of voltage, value of phase angle is phi R between this IR and VR. Then IR, the receiving end resistance will be in phase with the IR. So IR R by 2, IR R by 2 here is there, and IR X by 2 is again perpendicular to this. So directly then this will be connected. See from this diagram, VR and IR will be the reference. IR will be the reference, and VR will be a VR is can be calculated. VR and IR will have a phase displacement of phi R. So for the VR, we can add this drop. You are going to get the value of VC. So that value of VC they have obtained like this: IR R by 2, IR X by 2. If these two are this impedance drop they have added, so we are going to get that capacitance midpoint voltage is obtained. For this midpoint voltage, if you add it, for this midpoint voltage we can add it this value and these values, then we are going to get this Vs. So for this VC, IS R by 2, J times IS X by 2, if you add it, you are going to get Vs. But here, you can observe that this IC, this is the IC. So this value of IC, where you have to add it, this IR and IC will be added, you are going to get IS. So that they have taken IR, and this is the value of IC. Then these two will be added, we are going to get the value of IS. So VR, the resistance drop at the one end, from V resistance drop of the other end, the Vs. So like this, they have calculated the vector diagram. So VC is nothing but VR cos phi R plus J times VR sin phi R plus IR into R by 2 plus J times X by 2. This already I have explained. And IC is nothing but J omega C VC. So J omega C VC. And IS is nothing but IC plus IR plus J omega C VC. Then Vs is nothing but this drop plus the drop across this resistance, this impedance, Is into R by 2 plus J times X by 2. So with this, the vector diagram of medium transmission line, we can able to get it. Then what is the percentage regulation? As usual, VR dash by VR into 100. But VR dash, how we are going to calculate? VR dash is nothing but Vs into minus J by omega C by R by 2 plus J times X by 2 minus J by omega C minus J. That you can see that VR dash is nothing but this VR dash and this drop. Directly they are calculating Vs into division of voltage across the capacitance. It's a voltage divider. Two parallel paths are there. So how they are calculating is Vs, the total voltage into the amount of current passing through the capacitance divided by the total impedance. This will be the VR dash. So VR dash directly you can substitute, and VR is receiving end voltage divided by the receiving end voltage. We can get the percentage regulation. Then percentage efficiency, similarly percentage efficiency is P by P plus 3 times R by 2 into IR square plus IS square. No doubt here, because IR and IS are both are different. IR plus IC is nothing but IS. So so we have to calculate the losses across the half of the length of the line with IS current, half of the length of half length line losses with IR we have to calculate. So IR square R by 2 plus IS square R by 2 and three phases, so three times. So we are going to consider this. So where P is the three phase power delivered at the receiving end, R is the resistance per phase. Half of the resistance we have to take. The receiving end current loss and sending end current loss. Both we have to add it to get a total loss. We can able to write it as a two-port network. So when you are going to represent in two-port network, it will be like two-port ABCD parameters. So Vs is equal to A times Vr plus this already you know very well that it's a two-port network. So from the relations A is equal to here from the relations. This relations, from the relations we can say that A is equal to 1 plus yz by 2, B is equal to z into 1 plus yz by 4. You can simplify this A, B, C, D. You have to write the equation in terms of Vs and Is. In terms of Vr and Is. So we are going to get ABCD parameters like this, where Z is the total impedance of the transmission line R plus Jx, Y is the shunt admittance of the transmission line, that is 1 over J omega C. So this like this we can able to get the equivalent ABCD parameters for the medium transmission line if that capacitance is concentrated at middle of the line. It's a nominal T. Then we will go for the nominal pi. In the nominal pi model of a medium transmission line, the series impedance of the line is concentrated at the center and half of each capacitance is placed at the center of the line. The impedance is fixed and the capacitance is shared between two ends. One end is y by 2, other end is y by 2. So this is the look like a pi model. So we are going to consider it is a pi network. It's a nominal pi model. So for this, again we have to write the equations and phasor diagram. So again the phasor diagram we are see that IC1 is nothing but J times VR omega C by 2. From this equation IC1 is nothing but what is the value V by J omega, and similarly here IC2 is nothing but Vs J omega. Similarly IC2 also is the same Vs into omega C by 2. IC2. So I1 is nothing but IR cos phi r plus J sin phi r plus J omega r omega C by 2. IL is equal to IC1 plus IR, and IS is nothing but IL plus IC2. So these relations we can write it from that circuit, equivalent circuit. We are going to get these expressions. With these expressions we can write the phasor diagram. So IC1 is J times omega C VR omega C by 2. I1 is nothing but IR cos phi r plus J times sin phi r plus J times VR into omega C by 2. Vs is nothing but VR plus IL into Z. That Z already we can know that IR into cos phi r minus J sin phi r plus J VR. And IS is nothing but IL plus IC2. IC2 once again there, right? IL is already we have written like this. So we can substitute all these values. We are going to get Vs, Is in terms of VR and IR. In terms of VR and IR. So that we can take it here. VR. Initially we are going to take that IR is the reference. Then VR will be leads the voltage by phi r at phi r with respect to IR. Then the drop across the resistance is in phase with the IR, and similarly the drop across the reactance will be perpendicular to that. So we are going to get Vs. But here for the IR, we are going to add it IC1, then we are going to get IL. For that we are going to add it IC2, we are going to get IS. So like this we are going to calculate, we are going to get the phasor diagram of the medium transmission line. Then this can be written as equivalent ABCD parameters. But before that, the regulation VR dash minus VR into 100, where VR dash is nothing but Vs minus 2J omega C by R plus. This is the again parallel circuit. We have to calculate VR dash is nothing but the total voltage into the impedance one path J minus 2 into minus j by omega c by 2, that T2 is taken as numerator, minus 2j by omega c, r plus jx minus j by omega c2. This is the VR dash, receiving end voltage. So that under the full load condition, so that will be substituted here, and the no load voltage is here directly. You can substitute here. You can find out the percentage regulation. Then efficiency is nothing but similarly P by P plus 3 times IL squared R, where IL is nothing but IR plus IC1, or IS minus IC2. Anyone you can take, and equivalent of the ABCD parameters is VSAR, where A, B, C, D we can get it similar to the pi model, similar to the T model, same ABCD values will get. So that means that medium transmission line, in the medium transmission line, the capacitance is concentrated at the middle or concentrated at half of the capacitance at ends. Both are giving a same response and same values for impedance and admittance. So like this ABCD parameters also will be calculated for medium transmission line. Then the long transmission line, that long transmission line, the length of the line is greater than 160 kilometers. We are going to consider the resistance, inductance, and capacitance are not exactly concentrated at one place. They are distributed among all the throughout the length of the line, and are lumped at are assumed to be, for calculation purpose, we are going to assume that is lumped at one particular location, considered wherein parameters are assumed to be lumped. In the case of lines more than 160 kilometers long, for accurate solutions, the parameters must be taken as distributed uniformly along the length, as a result of which the voltage and currents will vary from point to point on the line. So, for the analysis purpose, we are going to consider like this. So, the parameters resistance, inductance, and capacitance will be distributed uniformly throughout the length of the line for a long transmission line. For the analysis purpose, what we are going to do is, we are going to consider for a small length of the transmission line. For this small length of the line, what will be the voltage is V plus delta V, and for the current is I plus delta I. And receiving end and the sending end currents are similar, and the length of the line is X. Yeah. So let Z is the series impedance per unit length, Y is the shunt admittance per unit length, L is the length of the line, Z is equal to Z into L is the total series impedance. L is the length of the line, Z is the per unit length, what is the impedance, per unit length, what is the admittance. So total is nothing but Z into L, Y is nothing but Y into L, total shunt admittance. Then this can be written like this, equivalent circuit is like this, Z into delta X, and admittance will be written as C into delta X, Y into delta X. Capacitance is written like this, and charging currents also will be there. So Y into delta X like this. So this is the equivalent circuit of a long transmission line. Voltage and current equations for long transmission line is V is equal to VR, V is equal to VR into E gamma S plus E minus gamma S by 2. These equations, derivations and all I am not taking care of, because here I am not going to explain how you are getting. These are the equations. This is voltage VR into that delta X values. Delta X, what is the voltage and what is the current, so that they have taken. Basically, V is equal to VR plus I into Z. I is equal to V into IR V into V by Z plus IR. So V is nothing but VR plus IR into Z naught. I is nothing but VR by Z naught plus IR. So these are the these values are basically due to due to delta X variation. Delta X variation are uniformly distributed length. How we are going to consider the equivalent values. ABCD parameters of the long transmission line. A is equal to cos H gamma S. Cos H gamma S is nothing but E gamma S plus E minus gamma S by 2. and B is equal to Z naught is shine gamma S. Shine gamma S is nothing but E gamma S plus E minus gamma S by 2, and similarly this cos and this is sine. So C is equal to 1 by Z naught into sine H gamma S. D is nothing but cos H gamma S. So this is the ABCD parameters of long transmission line. These values will be simplified. Means from this circuit only we can able to derive these equations. With these equations we can write it ABCD parameters. And for lossless line, that means R is equal to 0, G is equal to 0, ZC is equal to square root of L by C, where ZC is nothing but surge impedance, where ZC a pure resistance, and this is known as a surge impedance of the line. This will be explained in line. So ZC is nothing but for a lossless line. For a lossless line, the resistance is 0. When the loss is 0, losses are 0 means resistance is 0. So because of that, R is equal to 0. Then similarly, the conductance is nothing but 1 by R. So that also equal to 0. Then what is the impedance? What is the impedance is nothing but square root of L by C. So J omega L divided by J omega C, that omega J will cancel and L by C will be there. So ZC is equal to square root of L by C will be there. So this Z is known as a surge impedance. Z is known as a surge impedance. So here these are some of the effects also we supposed to carry out. What is the skin effect? And the skin effect is nothing but whenever the alternating current passing through the conductor, then the current density of that conductor is not uniform. The current in the electric current flows mainly at the skin of the conductor between the outer surface and the level called the skin depth. That means the distribution of current over the entire cross section of the conductor is quite uniform in case of DC system. That means whenever alternating current is passing through the conductor, then the distribution of current is going to be takes place uniformly in DC current, DC system. But in AC system, that is not the case. Non-uniform distribution of current is going to take place. Non-uniform means at the center point, it's the current distribution is small. At the outer surface, the distribution is the density of the current is more. So, but here the meaning is like this: the distribution of current over the entire cross section of the conductor is quite uniform in case of DC system. But what we are using an alternating current system, where the current tends to flow with higher density through the surface of the conductor, outer part, leaving the core deprived of necessary number of electrons. That means center point, you will not have maximum current distribution. At the surface only you will have. You can observe here, the conductor is there, flow of current is there. Whenever the AC current is passing, and whenever you will apply AC current, the current distribution at the surface is more than the center portion. This is a non-uniform distribution of current, non-uniform presence of electrons. So because of this, what will happen is at the middle low current density, at the edges you will have high current density. At the high current density, because of this, what will happen? In fact, in this condition, when absolute low current flows through the core, concentrating current depriving the core is referred to as skin of the. So because of this, what will happen? The resistance here, because of here low current density, here is a high current density. The resistance will be changing from center point to the outer part. Because of that, the resistance is increases. The resistance of the conductor increases at the outside. So this is known as a skin effect. So let us initially consider solid conductor be split this and all, okay, into number of annular filaments spaced indefinitely small distance apart, such that each filament carries an infinitely small fraction of total current. Like if the total current is equal to I, let's consider current to be split up into n filament current carrying current I, such that I is equal to n into I. During the flow of alternating current, the current carrying filaments lying on the core has a flux linkage with the entire conductor cross section, including filaments on the surface as well as those in the core. Not much important to this, that's why I'm not So the current being distributed in non-uniform manner, forcing the bulk of the current to flow through the outer surface or skin, giving rise to the phenomena called skin effect in the transmission line. Transmission line. See that outside parts. So, the skin effect in AC system depends upon shape of the conductor, type of material, diameter of the conductors, operational frequency. Due to that, what exactly happening because of this skin effect, the outer portion the current density is more, and inner portion the current density is less. Because of that, the resistance of the conductor increases. The current resistance sectional of the same conductor available for conducting low frequency AC resistance. Low frequency AC, high frequency AC. The alternating current density J in a conductor decreases exponentially from its value at the surface J according to the depth of the surface. Just that is current density, how it is changing. Then delta is called the skin depth. The skin depth is thus defined as the depth below the surface of the conductor at which the current density fall into 1 by E. That delta is nothing but square root of 2 rho by omega U. Rho is the resistivity of the conductor. Omega is angular frequency of current. Mu is absolute magnetic permeability of the conductor. So when the resistivity increases, then depth increases, resistivity increases. That is the meaning here. How to reduce the skin effect? Finally, what is the effect of skin is overall resistance of the conductor increases. To reduce that, what we have to do is increase the normal conductor survives A type of cable. That means material you supposed to vary. So that material is Lidge wire is used to mitigate the skin effect for frequencies of few kilohertz to about 1 megahertz. It consists of a number of insulated wire strands woven together in a carefully designed pattern so that the overall magnetic field acts equally on all the wires and causes the total current to be distributed equally among them. Basically, to avoid the skin effect, what we have to do is we have to use the bundled conductors or we have to change the type of material. Like more than one type of material we have to use to reduce the skin effect. That is the meaning in this. For getting that means bundle conductor. The bundle does not suffer the same increase in AC resistance that solid conductor of the same skin. To avoid the skin effect, we have to use the bundle conductor with the different materials. That is the meaning. So proximity effect. When the conductors carry high alternating current, then the currents are non-uniformly distributed in the cross-section area of the conductor. This effect is called proximity effect. When the conductors carry high alternating currents, the currents are non-uniformly distributed across the cross-section area of the conductor. Thus, proximity effect results in increment of apparent resistance of the conductor due to the presence of other conductors carrying current in its vicinity. Suppose the two conductors are nearby. Whenever the current passing through the conductor, heavy current passing through the conductor, then what will happen is the current distribution is not uniform in that conductor. So nearby conductor will have its effect. So what is happening is the resistance of that increment in the apparent resistance due to the current passing through one conductor, the effect will be in the other conductor. That due to that apparent resistance is going to be exist. So due to that, finally, what exactly is cross-sectional area of the conductor is increases. So when the two or more conductors are placed near to each other, then their electromagnetic fields interact with each other. Due to this interaction, the current in each of them is redistributed such that greater current density is concentrated in part of the standmost remote from the interfering conductor. So finally, what is the meaning is if the two conductors are like this, the current density is increases at the surfaces, and finally you can say that the area throughout the cross section of area, the current density is not uniform. That is the meaning. Half portion of the conductor is not at all having any current density, and half of the unit will have current density. When the conductor's current when the current is in the opposite direction, then this type of effect will be there. When the current in the same direction, this type of effect will be there. When the current, when the two conductors carries the current in opposite directions, this type of current density will be there. Current flow in the opposite directions. So, what are the factors which are affecting this proximity effect is frequency. The proximity effect increases with the increase in frequency. Diameter, the proximity effect increases with the increase in conductor. Then structure, this effect is more on the solid conductor as compared to the standard conductor because of the surface area of the standard conductor is smaller than the solid conductor. Because ACSR is multiple conductors will not have that addition that what you can say that apparent resistance in upon the material, depends upon the structure, depends upon the diameter, depends upon the frequency. This proximity effect is going to be affected. Frequency increases, proximity effect increases, diameter increases, once again a proximity effect increases, structure changes the proximity effect, and material also will increases. Then how to reduce the proximity effect using the different type of conductors can be reduced by using ACSR conductor. The steel is placed at the center of the conductor and aluminum conductor is positioned around steel wire. The steel increases the strength of the conductor but reduces the surface area of the conductor. Thus, current flow mostly in the outer layer of the conductor and no current is carried out in the center of the. Thus, reduces the proximity effect on the conductor. So, this ACSR conductor will mitigate the proximity effect. The effect in which voltage is the receiving end. Yeah. Next effect is Ferranti effect. The effect in which the voltage at the receiving end of the transmission line is more than the sending end voltage is known as the Ferranti effect. Generally, the receiving end voltage is less when compared to the sending end voltage because the receiving end side the load is existing always in between sending end to the receiving end. The number of loads will be there and the line drop will be there, voltage drop will be there. Because of that, receiving end voltage is always less than the sending end voltage, but sometimes the receiving end voltage is greater than the sending end voltage. This type of effect is known as the Ferranti effect. What is the reason for this is when the receiving end is open circuit condition or under light load condition. So Ferranti effect is due to the what is the Ferranti effect? Ferranti effect is due to the charging current of the line. When an alternating voltage is applied, the current that flows into the capacitor is called charging current. The charging current is also known as capacitor current. Increases the line when the receiving end voltage of the line is larger than the sending end. So whenever charging currents are there, these charging currents will additionally increases the capacitance value, and this causes the additional charging current. Then this total current will be increases, and when the total current increases, automatically the receiving end voltage is high than the sending end. Surge impedance. Then what is the surge impedance? Transmission line generates capacitive reactive volt amperes in its shunt capacitance and absorbing reactive volt amperes in its series inductance. The load at which the inductive capacitive reactive volt amperes is equal and opposite, such load is called surge impedance load. Generally, transmission line generates the capacitive reactive volt amperes and absorbs the reactive reactive volt amperes. So whenever this inductive and capacitive reactive volt amperes are equal and opposite, that type of load is called the surge impedance load. It is also called the natural load of transmission line because power is not dissipated in transmission. In surge impedance loading, the voltage and current are in the same phase at all point of line. When the surge impedance of the line has terminated, the power delivered by it is called surge impedance loading. So basically, the capacitive volt amperes is going to be generated by the transmission line, and the inductive volt amperes are going to be absorbed by the transmission line. When these both are capacitive and inductive reactive active volt amperes are equal and opposite, then that type of loading condition is known as surge impedance loading condition. So in that condition, the power is not going to be dissipated in the transmission. So when there is no power dissipation, then voltage and current will be in the same phase at all the point of that. So that type of condition, the surge impedance is that type of condition. Whatever the impedance is there, that is known as the surge impedance, and whatever the load is there, that is known as the surge impedance loading. Shunt capacitance charges the transmission line when the circuit breaker at the sending end of the line is closed. So this is shunt capacitance charges. Then capacitive volt amperes generated in the line is V squared by XC because capacitances are there. So V squared by XC or V squared omega C per phase. That is the capacitive volt amperes. Then these two will be get cancelled. Then V by I is nothing but is nothing but square root of L by C, and this is known as a surge impedance. Surge impedance loading is also defined as power load in which the total reactive power of the lines becomes zero. Total reactive power of the line becomes zero. Then that type of condition, loading condition, is known as surge impedance loading. So today I will stop here. Next class I will continue with this gate questions and remaining topics. So today I will complete. So I am leaving the class today.